Have you ever wondered how this car effortlessly stays in its lane, parallel parks on its own, stops at a stop sign, resumes its journey, all without any manual intervention? What makes these set of robots come into a desired formation from arbitrary initial conditions and track a reference trajectory? The hidden force behind all these technologies is the subject called control engineering. Hello everybody, my name is Ramkrishna Pasumarthy. I am a professor of electrical engineering at IIT Madras and I will be your instructor for the course on control engineering. The subject of control engineering finds many applications from connected and autonomous vehicles, robotics, as you have just seen some videos, IoT and smart cities. By the end of this course, you as a learner will be equipped with tools to analyze and design such systems which largely shape many things around us. Let us start with a little bit of introduction to this course. Some kind of language that we will use throughout this course will motivate ourselves with some examples before we build up a nice theory. Okay, so what is a control system? We have seen couple of examples and we'll slowly see how to understand, analyze and design controllers for such system. Let us start with some example. So this example is widely used in control literature. It's called the single tank system. The objective here is to maintain the liquid at some desired height level H star. The available information that we have is, we know that there is some water entering via the inflow and some water going out as outflow. I can measure what is the current level of the liquid. So can we manipulate anything to control the level? Imagine I am just filling water in a bucket, I switch on my tap, I mark a certain level, I switch off the tap when the water level reaches the desired value that I am looking for. Okay. So in this case, the additional thing is that you also have an outflow. Okay. So how do we control this system? Where there is some water being pumped in and also water being pumped out. What could be the basic control logic that one could think? And we do this kind of things in everyday life. First is increase the inflow when the level is below the reference. You want to pump in more water or put in more water into the tank, and decrease the inflow when the level is above the reference. If the water level is here, we may want more water to flow out of the system before it reaches the desired target. Okay. So assuming I do not have any outflow, I can just say, well, let the input, so I know what is my H star, I can measure the current height, and based on my desired level and the actual level, I decide whether how much water to pump in and at what rate. I can turn on the tap fully, then I try the tap a little lower to maintain maybe some lower level of lower amount of water flows in. So we can adjust the flow of water based on the level of the tap. That in control literature is called a constant gain. What happens when H star is Y of t, right? That my desired water level is equal to the actual water level, which means no need of more water. Okay, which means I just don't pump in any water, right? In that case, the inflow will directly be 0 mathematically also, right? H is equal to Y, H star is equal to Y, QIT will be K times 0 and QI will be 0. Okay. Now how do I account now also for the outflow rate? I just add another term, right? So whatever is taken care of by the difference between my actual and the desired, I also take into account how much is the outflow rate just by this simple mathematical expression. We will try to do a little more analysis on things like this and eventually try to understand how we write down system as a set of equations that will help us analyze better. Okay, the first step is how does one explain the dynamics of the system? What we see is I have a certain inflow and a certain outflow, and the difference of inflow versus outflow is what causes my height of the water level to increase, right? And this increases or decreases with time, right? So h is depending on time. So the variation of h of the height with respect to the difference in qi and qo can be captured as a as the rate of change of height. The rate of change of height of the water will depend on how much is the difference between the inflow versus the outflow. I measure the output as the height, and in some cases your measurements might be subject to some noise. Of course, we'll talk of this also a little later in detail. And this we will refer to as the single integrator model. Again, the details will follow. This is just a little introduction of how we can write down and analyze systems in different ways, starting from a differential equation to some kind of a diagrammatic representation. Okay, so something to think about. What did we see so far, and what did we learn? Well, it's good to ask ourselves some questions to see how much we have learned. So first question for you to answer is, what causes the level of water to increase or decrease in the single tank system? And what kind of conservation laws does this represent? So think in terms of conservation laws that you would have done in your school or early college, of conservation of energy, momentum, angular momentum, charge, flux, etc. The answer will be hidden somewhere during the lecture or during this entire week's content. Another important concept that we will look at this course is the concept of feedback. And this is, you see, again, this is not just a control systems or a very engineering concept. It's a very day-to-day concept. You go to a restaurant, just when they give you the bill or the check, they also give you a form to fill up, right? This is the feedback, rate the food, the ambience, the service, and so on and so forth. I teach a course, at the end you also can rate the teacher. You can rate not only the teacher but also how well the course content was done, how fast or how slow the course was conducted, the grades, and so on. Controlling temperature of a shower. I am recording this in a bit of a winter season. We see early morning we want to take a shower, we turn it on. So initially water is very cold, so I really go to the hot, turn my knob completely to the side, which gives me hot water. The water becomes very hot. Then I try to readjust 3-4 times until I get my desired temperature. And that also is a feedback, right? I sense the temperature as either being too hot or too cold, and adjust the knob between the hot and the cold based on what I sense and based on what is my desired. And I just do not adjust anymore when the desired temperature is equal to the sensed temperature. Looking at the mirror while dressing up, we do it every day. Cooking, I just check, is the food cooked enough, what is the level of salt, what is the level of spice, and so on. To more engineering systems or engineered system, air conditioner, we use this again very regularly. This system maintains the desired temperature by automatically switching on and off while you are above or below the desired temperature. When the temperature reaches the desired, the air conditioner switches off. If it's below, it again pumps in, if it's above, it pumps in more cool air to cool down the room. Geysers, we see, automatically switches off when the water reaches the desired temperature. Rice cookers also switch to warm mode after the rice is cooked. Cruise control, it maintains the speed. Suppose I set my cruise to a speed of 90 kilometers an hour and it's going on a flat road, very nice. I just encounter an uphill. Okay, then what happens? Well, the speed, naturally you would anticipate it to decrease. Now the automatic cruise control should sense that the car is going through an uphill and adjust its speed accordingly. Similarly for downhill conditions also, you just don't want the speed to accelerate to 120 as soon as it hits a downhill. Several other examples, speed governors in engine, they regulate the fuel supply to regulate the engine speed, glucose monitoring, and so on. What is what is the common feature of all these systems? In all these systems, there is a certain variable that is being controlled. The temperature, the speed, all these are measured by some sensor, okay, and this measured information is fed back to the controller to influence the control variable. As simple as on a shower, I just sense the my body senses the temperature. It causes me to act. If the water is too cold, it senses a signal back saying, okay, turn the knob more to the side which gives hot water. If the water is too hot, my body again senses that, and it tries to adjust it towards the cold side of the tap to make it closer to the desired temperature. Okay, so another concept which is also important is also of feedback. For example, if I look at my tank example, if there is no outlet, the problem becomes easier. I just kind of fill the bucket or the tank until it reaches the desired height and then stop. But there is something more happening here. There is QO. Some water is continuously flowing out of the tank. If I know the temperature, if I know what is the outflow rate, I can adjust my control accordingly, or the inflow rate, the way I deal with opening of my tap or the valve can be registered accordingly. If I see a speed breaker while I am driving a car, or if I perceive that there is a curve while driving, my natural reaction would be to slow down as I reach the curve and then speed up again. Similarly with the speed breaker. Studying for an exam, right? If I know that I have to prepare for an exam and so on, I start studying maybe a day before, 2, 3, 4, 5 days before and so on. Such systems are called feed-forward control systems. These are proactive. They take action before changes to the process variable can occur. So, in addition to feedback, we also have the concept of feed-forward. And the example that we started off with controlling the level of water in the tank takes care of both of these concepts. So you have a feedback coming from here which measures or which compares the desired height with the actual height, and there is, so you see a negative term here that's also captured here in the mathematical expression. So Qi is some k h star minus y. And so, and then you have the term which corresponds to the outflow of the water. Okay, so far so good. Then as a design parameter, I put k into my equation. But how do you choose k? Okay, larger k, you have response is faster. Okay, smaller k, if I just look at how you turn your tap, right? If you turn it on to the knob to the full throttle, there's a lot of water flowing. If you do it very slow, then smaller k will have slower response. In control terminology, you can also say that a larger k will have a larger noise amplification, possibly greater actuator wear if I maybe using my motor all the time at its full speed and so on. These concepts we will learn a little later. A major part of this course will involve in choosing what is the right gain, what is the right K, or designing different controllers according to the specifications and type of the process to be controlled. So we saw one example with a little bit of mathematics supporting my control objective. We will also later see of the examples of the car, examples of those robots and so on. Okay, what is the other concept in control? So if I take this example, so I have a fan, I have a regulator. All I can do is adjust the speed. If I put it at 0, we know that the fan doesn't turn on. 1, there is certain speed. 2, there is certain speed. 3, 4, and 5. Okay, so there is no feedback here. I just give an input at level 1, 2, 3, 4, 5 or 0, and the fan has its speed. There is no way that the fan can readjust its speeds based on the user concept. There is no feedback that is being sent. The output is not measured or compared with any other desired level, right? So the system's output does not have any effect on the input. If on the contrary, if I have an air conditioner, the room temperature increases from say 24 to 28 because somebody suddenly opened the door, there will be some mechanism that will sense that the temperature has increased, which will tell the air conditioner to pump in more cool air. Okay, that is a mechanism of feedback. In this case, there is no feedback. So the output doesn't really tell the input what to do to adjust to new circumstances. Similarly, a washing machine, even if I just put maybe a handkerchief or maybe a bunch of clothes, it just does its same program. It just pumps in the same water at some pre-adjusted level, minimum till maximum, whatever program I choose to wash my clothes. Gas stove, it doesn't really sense if my milk is boiling or the water is boiling and switch off. Similarly with microwave and so on. Okay, so few questions for yourselves to answer. I'll just take a few seconds pause. Okay, so based on this, how can we define a larger control system? So I have something that I will call as a plant or a process. So all this will be used interchangeably. So the plant I will call as the process, and also I will refer to this as system. Okay, so this will be interchangeably used and they will mean the same. So the first part is the plant or the process or the system that I would want to control. This could be several. This could be an automobile, a process plant, and a room with an air conditioner, economic growth, and so on. Then I have a controller. Controller here will be, it will be used to regulate a certain variable of interest, a temperature, pressure, inflation, speed of a car, and so on. So the controller will tell whether to, for example, pump in more water, increase the water level, decrease the water level. Controller will tell based on my inflation whether to change my interest rates going up or going down. Speed will also tell if I am maybe up the hill, then I may want to pump in a little more energy to maintain the certain speed and so on. The actuator is the one which will execute the command which the controller gives, like speed up or speed down, or pump in more water, or open the valve a little more, close the valve a little more, and so on. So these actuators, they execute the action, and these are devices which convert energy into some kind of mechanical motion in most cases. So you take an example of electrical motors, stimulators, servo motors, and so on. Now what does the controller do here in the feedback setting? So there must be some mechanism that will say, is my desired value of temperature or speed close to the actual value? Maybe I set my temperature to 24, but it's 27. Somebody should tell the air conditioner. So this mechanism is called a sensor. Sensor will continuously monitor a certain variable of interest, which we will call as the output. It will compare the actual output to the desired reference value, and based on that, the controller will compute what is a control what is a control signal. The actuator will change or will transform that control signal to an actual mechanical output, and the process keeps going. Two things that are undesirable here is the presence of noise in a sensor, and also disturbances. Disturbances in the form of say if the room is perfectly insulated, then we are fine. Suppose somebody just leaves a door open, or say 10 more people enter the room which I want to maintain a temperature to a certain desired value. Suppose I am also going in a cruise mode, I see an uphill or a downhill. That is also a disturbance, because my system has to respond to it and reject it to maintain its original or the desired speed. So what do we need to start with a given plant or a system or a process which we want to behave in a certain desired way? The process starts through learning of this course, right? So I have a plant which I want it to perform in a certain way. I design a controller such that it is insensitive to disturbances, possibly measurement noise, and so on. So the first step in all of these concepts would be to understand the process, the plant, the system that needs to be controlled. So, the next lecture we will start with understanding the plant. How do we, what are the different ways in which a plant can behave? Before I apply a control signal, I need to know what is the natural behavior of the plant. So, that will be coming up in the next lecture. See you then. Thanks for your attention.